Okay, so now we're going to talk about the alternating series remainder. So if a convergent alternating series satisfies the condition an plus 1 less than or equal to an, okay, that's what we showed, right? So each term is getting smaller. It's decreasing, it's non-increasing. Then what will be true? The absolute value of the remainder, which is denoted by R sub n, involved in approximating the actual sum S, I like to put a little fancy S here, by S sub n is less than or equal to the first neglected term. That S sub n is the nth partial sum, okay? So what does that mean? That is the absolute value between S and the nth partial sum, the real sum and the nth partial sum, is equal to the absolute value of the remainder. Which the stunning thing about the alternating series remainder theorem is that this is less than or equal to that first term that's neglected, the n plus first term, okay? So if you have that nth partial sum, you take the first n terms, and then that term right after the last one you used, you know, the remainder, that error, is less than or equal to that next term. Pretty interesting, okay? Pretty interesting. All right, so to kind of show you in a picture what's going on here, say you have this series and we want it to sum to S, okay? And so S is just some number here, okay? So I'm going to give you a couple different views here. So maybe the first sum is up here at S1. The next sum is down here at S2. The next sum is here at S3. The next sum is here at S4. And then S5. And then S6. And so on, right? Okay, so what's happening here is each S, each partial sum that goes out further and further is getting closer to that true sum, all right? So if I took like maybe, you know, S3, I went out to S3, that means that I got the first, second, and third, okay? So that S3 is the sum of those three terms, okay? Now, the remainder would be what? The remainder would be this difference, R3 here, okay? Which is how far we are away from the true sum. Now that difference, that vertical difference, that R3 there, okay, if we're kind of going to zoom in here, is less than or equal to, okay, that A sub n, that nth term, okay, so that nth term, that next term, so not S4, but really it's, if you thought about this, because S3 is like S1 plus S2, and then plus, well, I guess that might be it. Well, let's see. Let me back out of that. I don't like that. Okay. This is less than or equal to that A3 plus 1, which is A sub 4. Okay, so that fourth term there. So that fourth term, we don't have it. That's what was messing me up there. These are sums, okay? So they're not our ANs. So we got to think a little bit differently about it. So one thing that might help you out a little bit, I can draw in another picture. Instead of being in 2 dimensions, let's just do 1 dimension, okay? So maybe this is my target, right? This is what the series is going to limit to. The first term I get, A1 gets me here, okay? And then, maybe over here is 0, okay? Well, maybe, all right, let me erase that. Maybe the first term is a little bit too big, and it gets me here, it gets me A1. So that's like my positive term. But then the next term, A2, is negative, okay? So the negative 1 shoots me back over here. So this is, so let me do this, because I'm still messing up here. Sorry about this, guys. This is what happens when you do things on the fly, okay? So maybe the first term is really big. It overshoots. All right, so my S1 is over here. But then the next time I add 1, I subtract, and it bounces me back to over here. But then I add again, and it bounces me over to here. But then I subtract, and it bounces me back over to here. And then I add again, and it bounces me back over to here. And so on until we get closer and closer. So what's happening here? I start at 0 and I add, and then I subtract. And then I add, and then I subtract. And then I add, and then I subtract. And I add. And you see how we've kind of got this vortex that's sucking us in to the actual sum here. Okay, so that's kind of what's going on there. So let's try to do like a mini proof of this. Okay, so proof. So Rn is equal to S minus Sn. Okay, that's by definition, right? This is going to be the series as n goes from 1 to infinity of -1 to the n plus 1 an minus the series, and let's do n equal 1 to capital N, the nth partial sum, right? n plus 1 to the an, okay? Remember, this is only the nth partial sum. That's why we stop at that capital N there. So what is this going to do? What is this going to do? You've got all your terms, but what's going to happen is this is going to knock out, this right here knocks out first n terms. Okay, it knocks out the first n terms. So what's left when I knock out the first n terms? Well, that's -1 to the capital n plus, well, this was the n term, so n2 a n1 plus -1 capital N3 a n plus 2, and so on and so on. Now what can I do? I can factor a -1 to the n out of all of these. And what do I have left? I have capital N plus 1 minus a capital N plus 2 plus a capital M plus 3, right? And so on and so forth. Okay? So what is this? Well, this is telling me now take the absolute value Okay, so Rn is equal to an plus 1 minus an plus 2 plus an plus 3 minus dot dot dot, right? And what is this equal to? This is equal to an plus 1 minus an plus 2 minus an plus 3 minus an plus 4 minus an plus 5 minus dot 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 less than or equal to. Okay, what is that less than or equal to? All these things that I'm subtracting here, okay, they're taking away. So that's less than or equal to a sub capital N plus 1. And that is what we are trying to show here. All right, pretty slick thing going on here. So now let's run through an example. So here's your example, typical homework or test problem. Show the series is convergent. Okay. How many terms of the series do we need to add in order to find the sum to where the absolute value of the error is less than 0.00005. All right, that's what the goal is. I'm trying to make my error as small as I can. All right, so here's the series. N equal 1 to infinity, negative 1 to the n plus 1 over n to the 6. Why is this important? Well, you know what? If you're traveling from here to Nacogdoches, it's probably not that important. But if you're traveling from Houston up to the moon, then if you're off by just a itty bitty bit, then you could miss the moon by a ton of miles. Okay, so that's beyond my pay grade to calculate. But the deal is, when you're talking about traveling far distances, being off by the slightest error could cause some pretty big issues. So it's very important that we can program computers to say, we want to set a tolerance level here. All right, calculus is what allowed us to get to the moon. This is what it's talking about here. Okay, it allows us to be as precise as we need to be to get the problem done. So what do I need to show here? All right, so note an plus 1 less than or equal to an. How do we know this is true? Well, what is that? That's 1 over n plus 1 to the 6 less than or equal to 1 over n to the 6, right? Here, your an is 1 over n to the 6. Okay, this is just a sign changer, right? So is that true? Well, if n is greater than or equal to 1, okay, then I'm pretty sure this is going to be true, isn't it? So less than n to the 6 less than or equal to n plus 1 to the 6th. Yeah, I think so. Since n is okay, since n is greater than or equal to 1, 1 is greater than or equal to n to the 6th, right? And then we're cooking. Okay, this is true. All right, so we're good to go here. So all of these are greater than 0, all right? This is true for n greater than or equal to 1. So all we got to do now, since we've just shown that it's non-increasing, is we need to take the limit as n goes to infinity of 1 over n to the 6. Well, guess what? That equals 0. That one's pretty easy. Therefore, by the alternating series test, the series n equal 1 to infinity, negative 1 to the n plus 1 over n to the 6 converges. Now that we know that it converges, what we need to do is figure out what level we got to get to, okay, to make our error less than 0.00005, okay? So let's look at the sum. This is equal to 1 over, if I plug n equal to 1 in, I get 1 over 1 to the 6 minus 1 over 2 to the 6 plus 1 over 3 to the 6 minus 1 over 4 to the 6 plus 1 over 5 to the 6 minus 1 over 6 to the 6 plus, and so on. Okay? This piece right here gives me 1. This piece is 0.0156. This term is 0.00137. This term is 0.00024. This term is 0.00064. That was close. This term right here is going to be 0.00021. Bingo. All right. So this last term here, ooh, can't see that with that highlighter. So this last term here is less than 0.00005, which is what we were looking for, right? Okay. So let's think about this for just a second. Okay? What's our theorem say? All right, so I want absolute value of S less than what? Sn, okay, to be equal to absolute value of Rn, which is less than or equal to An plus 1, okay? So my error term, okay, this is A1, so A1, A2, A3, A4, A5, A6. Okay, A6 was the one that was finally less than this value that I wanted, right? So A6 here, what number do I plug in for n to get A6? I plug a 5 in, n equal to 5. So that gives me A5 plus 1, that's A6. Okay, so that means I need R5. And this is equal to S minus, so the sum, the true sum minus S5. Okay. Now, this remainder, okay, A6 is roughly 0.00002. Right? This is definitely less than 0.00005, which is what I wanted. All right? So, since the sixth term is less than the desired error, then we need to add the first 5 terms, not times, terms, to get the desired accuracy within 0.00005. Okay? So how many terms did we need? We need 5 terms to get the desired accuracy. All right, another way that you can do this besides just muscling out the calculations is through some algebra. Because what if it's like it takes like 100 terms? You don't want to have to walk out and do 100 terms, okay? So a way to shorten it up, a shortcut for you, okay, is take n plus 1, which is equal to 1 over n plus 1 to the 6th, and set that equal to your tolerance, 0.00005, okay? When you solve this, right, and so you're going to need your calculator maybe to solve this. So when you solve that, what is that going to look like? Well, let's see here. This is a total mess, huh? Let's go to our calculator. So I'm going to do 1 divided by parentheses, x plus 1, close parentheses, to the 6th. That's one graph. And I'm going to do another one at 0.00005. Enter. Okay. So what I want to do... Oh my goodness. This is going to be impossible to see. All right. Let's see if I can calculate the intersection. Good luck, huh? Okay, so left bound, right bound. Oh my goodness. Okay, let me try this again. Second calc, calculate the intersection. So left bound, right bound. Okay, so x equal 9.75. Yikes. All right, that is not correct. Okay, so we're gonna have to get out of this and just use our head. Okay, 0.00005 in fraction form, math frac. That's 1 over 20,000. Okay, so I have 1 over n plus 1 to the 6th equals 1 over 20,000. All right, cross multiply. I'm going to have 20,000 equals n plus 1 to the 6th. Okay, so I need to take the 6th root of 20,000. Okay, 6th root of 20,000. What in the world is that? So 20,000 raised to the parentheses 1 divided by 6, that's the 6th root. Okay, so that's like 5.21. So that's like 5.21 roughly. And then we'll minus 1 to both sides. So n is approximately 4.21. Okay? Now, can you have 4.21 terms? No, you cannot. So to be at the desired accuracy, okay, you round up. Round up. So n rounds up to 5. There's 5 terms needed. And that is exactly, my friends, what we discovered here. We needed 5 terms. Why did it come out to that decimal? Well, if you noticed when we were writing out these terms here, this was like, oh, that's not going to work. Let me do something. Oh, that's just not good at all. Okay. This is 0.00064, and that was 0.000. Oh, I'm sorry. I'm looking at the wrong one. 0.00021. Okay? So this one definitely got the job done. This almost did it, but it was just shy, right? It was just shy of working. So we needed a little bit more than 4 terms, and that's where that 2,1 was coming in. But since you can't have a little bit more than 4, you need at least 5 terms, okay? So that's the error going on there. So this is just another way to work it. Reverse engineer by figuring out, set your tolerance level equal to that nth term. So if an is equal to 1 over n to the 6th, then an is this 1 over n plus 1 to the 6th. And solve for n. If you get a decimal, round up. Okay? Always round up if you end up getting some type of decimal there. So that's just, let me show you the whole thing in one view. All right, guys.